In this video, we are going to take a look at the combined gas law. The combined gas law is an equation that basically takes Charles' law, Boyle's law, kind of puts them all together in the terms of the three variables, which we're talking about: pressure, temperature, and volume. So let's go ahead and write out mathematically what the combined gas law is. So mathematically speaking, the combined gas law is P1 times V1 all over T1 is equal to P2 times V2 all over T2. Alright, so let's kind of explain what these mean. So P stands for pressure, V stands for volume, and T stands for temperature. The little subscripts that I've written here, the 1's and the 2's, basically indicate your initial and your final conditions. Initial meaning what you're starting out with, and final meaning what you end up with. So the 1's in this case are going to denote our initial conditions, or the conditions that we're starting with, and the 2 denotes the conditions that we end up with, or the final conditions. Okay, so like we've said, the combined gas law takes pressure, volume, and temperature and puts them all in a nice neat little equation that kind of relates all three of these variables together. So now that we've got a formula for the ideal gas law, let's go ahead and scroll down and let's work out a problem. So this first problem says that a sample of sulfur dioxide occupies a volume of 652 milliliters at 40 degrees Celsius and 720 millimeters of mercury. So what will the, there actually should be another L in the wheel, so let's kind of draw that there. Okay, so what volume will the sulfur dioxide occupy at STP? Okay, so let's go ahead and go through. We have a volume, my 652 milliliters, so we've got a volume, and we've got a temperature, and we've got a pressure. So let's go ahead and jot down what our ideal gas law is, or not ideal, sorry, the combined gas law. So we've got P1 V1 over T1 is equal to P2 times V2 over T2. Okay, so if we read here, it says a volume of 652. So that is our first volume. So this is an initial volume. So we're going to take 652 and we're going to put in place of V1. So I'm just going to write here down below. So V1, let me go over to the right and have a little bit more room. So we said 652 milliliters is going to be our V1. So that is our first volume. So I'm going to go ahead and put parentheses around this. So if we keep reading, it says at 40 degrees Celsius. Well, this is our initial temperature, 40 degrees Celsius. But when we're dealing with gases, we cannot use Celsius as a unit. We must convert Celsius to Kelvin. And if you remember, the formula for converting Celsius to Kelvin is Kelvin is equal to C, which is Celsius, plus 273. So all we have to do is put in 40 for C, so we'll say 40 plus 273 is equal to K. So our first temperature, K, is going to be equal to 313 degrees Kelvin. So this number, the 313, is going to go in place for T1. So I'm going to go ahead and draw my line here. So T1, I'm going to put 313 Kelvin. So that goes in the bottom. So I'll put parentheses around it just to kind of be consistent. So the next thing that we're having here is pressure. So if we look up here and keep reading, pressure is 720 millimeters of mercury. So that's going to go up here. So we're going to say 720, and my units are mmHg, so millimeters of mercury. So I'll put my parentheses here. Alright, so now we've found our initial conditions. So the left-hand side of the equation is our initial conditions. So now let's keep going. It says, what volume will the sulfur dioxide occupy at STP? Well, we know we're looking for volume, so let me go ahead and put in V2, because I know that's what we're going to be looking for. So we'll put that in parentheses, and we're just filling in the rest of the things. So STP. STP stands for standard temperature and pressure. So we're looking for standard temperature and standard pressure. Okay, so I'll abbreviate these. So standard temperature and pressure. The standard temperature for a gas, we are going to use 273 degrees Kelvin. Okay, so whenever you see this STP, it stands for standard temperature and pressure, and the number that you're going to use for temperature is 273 K. The standard pressure, the pressure that we are going to be using here, standard pressure, often you'll see it in atmospheres. So standard pressure is equal to 1 atmosphere. But in this particular problem, they've given us millimeters of mercury as our unit of pressure. So if you remember, the conversion factor between 1 atmosphere and millimeters of mercury is 760 millimeters of mercury is equal to 1 atmosphere. So at STP, if I'm using atmospheres for my units, it's 1, but if I'm using millimeters of mercury, it's 760. So we're going to go ahead and put 760 millimeters of mercury in for our standard pressure. So we'll put parentheses around that. And our standard temperature was 273, so the 273 goes in the bottom. So we've got this, and we'll put parentheses around here. So now, this is probably the most difficult part, actually setting it up. So once you've set it up, it's just multiplication or simple algebra after that. So once you've got this, we're going to go ahead and cross multiply, and then we're going to divide. So I'm going to switch colors here. I'm going to grab, let's say, this kind of teal color. So here we're going to say 313 times 760 times V2. Now, because we've got this, we're basically multiplying 3 things together because we've got 3 different variables. So we're going to take the 313 once again and multiply by 760, and we're going to multiply by V2. And when we multiply those out, we're going to get 237,880 times V2. Now, don't freak out if you get really big numbers because, you know, we're multiplying three-digit numbers here. So our numbers are going to get kind of large, especially for this particular side when we're multiplying these and then this number on the bottom. So when I multiply 313 times 760 times V2, this is what I get, 237,880. And then when I multiply 273 times 652 times 720, for this number I get 128,157,120. So like I said, these are really big numbers, but don't let it freak you out because we're going to get big numbers because we're multiplying 3 numbers that have 3 digits. So now to solve this equation, all that we have to do is we have to divide this side by 237,880, and we're going to divide this side by 237,880 also. And once we do the arithmetic here, we're going to find that V2 is actually equal to 538, and we'll round to 1 decimal, we'll say 0.7. So 538.7, and this is volume. Now the first volume that we started with was 652 milliliters. So whatever unit we start with on the left, we have to keep on the right, so I know that my unit for volume here is going to be milliliters, so the answer is 538.7 milliliters is my final volume. So let's scroll down and let's try one more problem. So here it says a gas has a temperature of 14 degrees Celsius and a volume of 4.5 liters. If the temperature is raised to 29 degrees Celsius and the pressure is not changed, what is the new volume of the gas? Kind of the beauty of the combined gas law is you really are only dealing with one particular formula, and if there is a variable that stays constant, let's get rid of that. If there is a variable that stays constant, we can essentially throw it out of the equation, as you'll see in just a second. So I've got my formula written out. So P1 V1 over T1 is equal to P2 V2 over T2. So I'm going to go ahead and switch colors here again. So if we're reading, this says the pressure is not changed. So if the pressure is not changed, I can go ahead and mark out my pressures because with the equation, if it doesn't change, whatever the pressure is on the left, it's going to be the same on the right. So they essentially cancel one another out, and because they don't change, we really don't want to complicate our calculations, so we just throw them out. Plus, they don't even tell us what the pressure is. So we just take the P out of the equation, and we're ended up with V1 over T1 is equal to V2 over T2. Now let's go ahead and start plugging in our values for volume and temperature. Well, let's see. A gas has a temperature of 14 degrees. So we know that 14 degrees is going to be our initial temperature. But once again, we can't use degrees Celsius. We have to use Kelvin. And Kelvin, as you recall, Kelvin is equal to Celsius plus 273. So if I take 14 and add to 273, I'm going to get, let's see here. So we're going to take 14 plus 273. And then we're going to get 782. So we get 287 Kelvin. So that is going to be our T1. So I'm going to say 287 Kelvin, and I'm just filling this into the equation. So now we have to find our first volume. So our first volume, and a volume of 4.5 liters. So 4.5 liters goes in our numerator. Okay. Let's see. Let's make that look a little better. So 4.5 liters. Now we have to find our final conditions. So it says, what is the new volume of the gas? Well, that means we're looking for volume 2. We don't know what the new volume is. That's what we're looking for. So now T2, what is the final temperature? It says the temperature is raised to 29 degrees Celsius. So once again, they give us the degrees in Celsius. So we're going to take 29 degrees Celsius, and we're going to add that to 273. And then when we add this together, we're going to get 9 plus 3 is 12. Carry the 1, so that's going to give us 10. Carry the 1 again, so 302 degrees Kelvin. So that's what's going to go in the denominator here, so 302 K. So now once we've got this, the next thing we do is we cross multiply and divide. So I'm going to take 287 times V2, which is going to give me 287 times V2. And then I'm going to take the 302 and multiply that by 4.5, and when I take 302 times 4.5, I get 1,359. Alright, so at this point, the next thing that we have to do to solve for V2, we're going to divide this side by 287, and then we divide this side by 287, and we get V2 to come out to be 4.74. Now, if we're going to look at the units, this is volume is measured in liters. That's what we started with, was liters. So we're going to keep the same unit on our final answer. So it's 4.74 liters is our final answer. And that actually kind of makes sense because we know among pressure, temperature, and volume, if we hold pressure constant, when we increase temperature, volume is going to go up too because they're directly proportional to one another. So in the problem, it says that the temperature is raised to 29 degrees Celsius, so the temperature increases, so we would expect the volume to increase. So if we compare volume 2, which is 4.74, to our initial volume, which is 4.5, we do in fact see that volume 2 has increased over the 4.5. So our mathematical relationship here holds true, and it's just kind of validated by the final answer that we get in the 4.74 liters.